My name's Russ Klein, and I work for Siemens EDA in our high-level synthesis group, and I'm going to be talking to you today about accelerating RISC-V with high-level synthesis. Now, everyone here in the audience is aware that the demand for compute capability continues to increase. If we look at video data rates, I was at the Consumer Electronics Show in Las Vegas a couple months ago. Instead of looking at 4K TVs, we were looking at 11K and 16K. I'm sure they're working on 30K at the moment. And we're getting higher frame rates, more frames per second. So there's a lot more data to process. Devices are getting smarter. Our embedded devices, we expect to gesture at them, talk to them. We want them to recognize us. And inferencing is going to move into edge devices. We're going to see millions, billions, even trillions of floating point operations that are going to need to take place on device. Network rates are going up. 5G increased the total data rate by over 100x. It's going to go even higher with 6G. And in the face of this, general purpose compute processors are reaching their limits. Now, Moore's Law, the orange line there, that's continuing up. We can still build more transistors in the same area of silicon. We're going to go down to 3 nanometer, 2 nanometer, even 1 nanometer. We'll have more transistors. But if we look at what's happening in the processor space, general purpose compute on a single thread is just not increasing anymore. There's a lot of reasons for this. Part of it is when Dennard scaling broke down and the power density issues that we've got. There's also the memory wall. And we're also seeing a reduced return on investment for putting new features into a processor, the processor architecture, to increase throughput. Now, since the end of Dennard scaling, processor vendors have basically just been stamping out more cores. But that doesn't help if you've got single-threaded software. And the software community continues to build single-threaded code. And the dirty secret is that software is really slow and inefficient. The programmer's model that we impose on anything running on a CPU severely limits our ability to bring in parallelization. As an example, a rocket core, which is one of the basic RISC cores, running a convolution algorithm. Convolution algorithm is commonly used in image processing and artificial intelligence. It does successive multiply accumulates. A rocket core running in software is going to generate one of those multiply accumulate operations every 25 clocks. We do the same thing in hardware. We can run 25 multiplies concurrently in a single clock. That's 525 times faster. Bringing in parallelism is extremely powerful. The other thing is that big processors are exponentially power inefficient. If we go to a very small RISC-V, it's going to be able to use a very small amount of energy to perform a computation. As we go to bigger and bigger implementations, we're going to use exponentially more energy to do that same computation. So we can't simply just build a bigger processor to get out of this problem. And for a lot of systems today, even if you got the biggest processor available, it wouldn't have enough horsepower. So what do we do about these problems? Well, Dave Patterson, who founded the RISC-V consortium, basically says the answer is domain-specific architectures. He advocates for heterogeneous compute based on a RISC-V base architecture, and then extending it with accelerators. And the accelerators would be ISA extensions, new processing elements, new instructions, coprocessors, and even external accelerators. He views this as the new golden age for computer architecture. It's a talk that he's given a number of times, but basically no longer are we going to try and make a single CPU address all the problems. We're going to customize the CPUs for very specific problems. And that's how we can continue to get greater performance and greater efficiency as we move forward. High-level synthesis is a technology that's going to allow us to take software-based representations and turn them into accelerators through compiler technology. And as we do this, High-level synthesis is going to be able to give you feedback on what does the performance look like, how much area are we going to take up, and what's the power consumption going to be very early on in the design cycle, so we can decide, do we keep that accelerator? Do we change it up a little bit? Exactly what do we do? As I said, high-level synthesis is a compiler-type technology that takes a representation of an algorithm, typically in C or C++, but some of the high-level synthesis companies are looking at doing Python and other procedural languages. It takes that as input and generates synthesizable RTL as an output. Synthesizable RTL can be taken downstream by the traditional hardware design tools all the way out to an FPGA bit file or an ASIC GDS2 file. High-level synthesis works by parsing your original algorithm in its original language and creating a global controlled data flow graph. And from that, it analyzes it to identify parallelism and data dependencies so that it can restructure that into a set of state machines and data flow logic that implement that exact same function. Then it creates a set of synthesizable RTL based on the user's directives for what type of architecture does it want for that algorithm. Are we going to unroll loops? Are we going to share resources? What algorithms are we going to pipeline within that? And it also understands the target ASIC technology or the FPGA device that we're going to build this for, and the target frequency that we want to run that with. High-level synthesis allows people to design a lot faster than at the RTL level. If you're designing at the RTL level, you're describing every single wire, every single register, every single operator. When we design with high-level synthesis, we're describing an algorithm. And that means the compiler can do all of that detailed work for us. Our experienced users are able to create designs about 10 times faster than traditional RTL flows. And when we go from project start to project tape out, it can be 4 times faster. Part of the reason is we have much faster verification. If you look at the traditional RTL verification, you're trying to verify functionality down at the level where we've described every single register and every single operator. If we verify functionality at the abstract level, we can test it out much more quickly, and then we can prove equivalence between the abstract model and the RTL model. And in doing that, we can reduce our verification time dramatically. And we do that with both formal equivalency checks between the C and the RTL, as well as dynamic verification. We can also retarget to different technologies or different clock frequencies with the change of some compiler settings. Now I'm going to touch on a few real-world examples that we've gone through in taking algorithms that were running on a RISC-V processor and turning them into accelerators. So the first one is a set of new instructions that were added for an AI data type that someone defined. Then I'm going to talk about a SHA-256 hashing algorithm that was built into a coprocessor and attached to a rocket core. And then I'm going to talk about an inferencing accelerator that we built. So the folks over at Google who work on artificial intelligence, both inferencing and training, and build the TPUs, they came up with a new data type called, it's a 16-bit floating point called brain float or bfloat 16. It's a much smaller representation, but it's got all of the precision and all of the dynamic range needed for most artificial intelligence inferencing and training applications. Because it's 16 bits instead of 64, you've got a lot less memory, you need a lot less bandwidth moving the model parameters and the features around. And so they shrunk this down. It's what they use internally on their tensor processing units. We looked at that and said, boy, wouldn't that be kind of cool if we could make instructions for a RISC-V processor that did addition, subtraction, multiplication on this new data type. And so we constructed those in C++ and then built each of the instructions and then tied it back into a RISC-V processor. The resulting implementation we built into a SIMD instruction where we took 4 of those 16-bit values, packed it in a 64-bit register, and then we could do 4 adds or 4 multiplies in parallel. The resulting implementation ran inferencing and training 5 times faster and used about 12% of the energy. And these were just new instructions that got compiled into the RISC-V processor. The next example that I want to describe is a coprocessor that we built for a SHA-256 hash coprocessor. So this has a bit more computational complexity to it. We're going to be doing millions of low-level bit operations on a set of data that we're trying to create this hash for. When we try and do this type of operation on a traditional CPU, it involves a lot of shifting, a lot of masking, perform an operation, shift it again, mask it back in. And these are really inefficient on a traditional CPU architecture. By pushing this into a coprocessor, we could do all of those bit manipulations in parallel. Bit shifts just become wires, and it becomes much more efficient. This is a highly parallelizable algorithm, and so pushing it into hardware made a lot of sense. We took the algorithm, a reference definition, and ran it through our high-level synthesis compiler and put a coprocessor interface on it. And then using coprocessor instructions from the RISC-V, we were able to compute the hashes 25 times faster and using about 2% of the energy to perform that hash. The last example that I want to touch on is an AI inferencing accelerator. Here we were building an accelerator that took the convolution routine as well as the vector matrix multiply and accelerated them on a bus-based accelerator. This was done for an object recognition algorithm called YOLO-Tiny. And it's an algorithm that will put bounding boxes around pedestrians and bikes and cars, and you've seen lots of examples of this. It's a very efficient one. It only runs 3.4 billion multiply accumulate operations per inference. But it's got some very large intermediate data sets in between high tens of millions of megabytes to hundreds of millions of megabytes. And that intermediate data set, we needed to have the peripheral access the system's memory to hold all of those. But ultimately, it's a very highly parallelizable implementation, and we were able to put an array of multipliers in place, and we reduced the overall data movement that needed to be done, which typically becomes a bottleneck and is extremely power costly. Ultimately, we were able to run this algorithm having both the convolution accelerated as well as the vector matrix multiply, but all of the remaining operations were done in software on the RISC-V processor. We ultimately ran over 1,000 times faster and used about 1,500 times less energy per inference. Now, when I talk about this technology to the RISC-V audience, one of the questions I often get is, well, why not just do that in Chisel? Chisel kind of works for that. And it's true that both Chisel and high-level synthesis allow a designer to work at a higher level of abstraction. You can run functional verification much faster on the design, and both environments require the skill of a hardware designer to be successful building things. But high-level synthesis creates that control data flow graph and understands the entire algorithm, and it can manipulate that. So if we want to share a multiplier between 3 different parts of the algorithm or create unique multipliers for each of those, we can do that with compiler settings. You just can't do that in Chisel. Chisel is really a hardware description language where we're still describing every single register and every single connection. We've got clever ways of unfolding it, but it doesn't have global knowledge of the algorithm. And so high-level synthesis has a greater ability to customize it and share or replicate different parts of the design and do it more efficiently. So high-level synthesis is going to allow us to take the base RISC-V architecture and extend it with accelerators that can offload the heavy lifting that we're doing within our application. And these can be customized for specific domains, making for domain-specific accelerators. And high-level synthesis gives us an understanding of the impact of that partition in terms of power, performance, and area that we're going to be using up, so that we can make informed design decisions as we create this new implementation. And it enables us to achieve higher levels of both performance and efficiency than would be possible with just a software implementation alone. All right. Thank you for coming out and listening to my talk this afternoon. Are there any questions that anybody's got?